Hi everyone, in this tutorial I will update the previously described method for assigning lower limb landmarks used to detect characteristic alignment angles. In particular, I revised the landmarks related to the tibial plateau and the tibial plafond. Instead of assigning 4 points for hemiplateau, we will annotate the rim, the margin of each hemiplateau, specifically in the region covered by cartilage, while avoiding the insertion areas of menisci and ligaments. In the scene, 5-point lists are already present. We will start with the medial tibial plateau rim. The points will be placed directly on the 3D model. However, the standard views, especially coronal and sagittal views, are very helpful for accurate identification. Enabling the crosshair also helps to localize the correct points. For explanatory purposes, I am going around the rim and highlighting some regions in the coronal and sagittal views. To improve reliability, it is recommended to follow the rim along local maxima, avoiding points that fall too far inside the plateau or too far outside. In correspondence with the tibial spine, we try to follow the base contour. Pressing a point while keeping the Shift key pressed allows you to visualize its position simultaneously in the 3D view and in the standard views. There is no minimum of maximum number of points. The only requirement is that they uniformly describe the rim. The order of point placement doesn't matter, as the code automatically recognizes their spatial distribution and performs resampling before applying principal component analysis. After a double check, we can proceed with the lateral tibial plateau rim. Again, for clarity, I will go along the rim to highlight its contour on the 3D model as well as in the standard views. The rim and its local maxima can be identified using both views. As on the medial side, in correspondence with the tibial spine, we aim to follow its base. As with the medial rim, there is no predefined number of points and their order is irrelevant. Compared to the medial rim, the anterior region of the lateral plateau is more challenging as it smoothly decreases toward the center and anterior portion of the tibia. We should avoid this area, which corresponds to the meniscal root attachment. Finally, we can perform a double check and refine the point positions if necessary. Instead of previously assigned 4 points on the tibial plafond surface, we now define 3 point lists. The first one, tibial plafond rim, follows the same principle as for the hemi-plateau. We assign an appropriate number of points to cover the contour of the tibial plafond, with one minor exception. We avoid placing points on the medial facet of the medial malleolus. In this area, as with the tibial spines, we aim to follow the base of the distal tibia. It is useful to check the margin both in the 3D view and in the coronal and sagittal views. After a quick review, we can start placing the landmarks to cover the entire plafond. The code will use these points to calculate the center of the tibial plafond. We can double check and still move the points wherever we prefer. The principal component analysis performed on the tibial plafond rim doesn't match the distal tibial axis because a prominent region in the anterolateral area tilts the principal axis too much. For this reason, we choose a slightly more proximal slice just above the ankle articular surface to assign the last two landmark lists, distal fibular rim and distal tibia rim. This slice is easily recognizable as the one immediately above the distal tibial surface, including the entire tibial cross-section. Once we are on the correct slice, we first assign the points along the fibula bone contour and then, after selecting the last markup, place points along the tibial bone contour. The number of points is not critical, we just need to cover the margin. We still have the option to make adjustment at the end. The code will perform principal component analysis on these landmarks, and the resulting principal axis will correspond to the distal tibial articular line.